let's go through the final question here. So the final question is saying propane burns according to the following equation. We're lucky this time. It's giving us the equation. We don't have to write it out or balance it. And it's saying what volume of oxygen at 20 degrees Celsius, 102.6 kilopascals, is used if 640 liters of carbon dioxide is produced. Now here's the important thing. It tells us that the CO2 is also measured at 20 degrees Celsius and 102.6 kilopascals. So, because the conditions are the same, we don't have to do any conversions. We are going to just do straight up stoichiometry here. So for part A, we're going to go with the 640 liters of carbon dioxide that's given, and we're going to multiply that by our mole ratio, or in this case our liter ratio. So for every 3 liters of CO2 gas, we're looking at 5 liters of oxygen. And let's see here, that is 640 times 5 over 3, that is 1066, and we are looking at 3 sig figs, so let's round that to 1070 liters of O2. Alright, part A is pretty easy. Part B is a little tricky. Let's go through this one. Okay, so for part B, we are given our volume in milliliters, so the first thing we need to do is convert that. So we've got 465 milliliters, and for every 1 liter we have 1,000 milliliters, so that conversion comes out to 0.465 liters. And we're also given a temperature of 37 degrees Celsius. We need to add 273.15 to that to get our Kelvin, which is 310.15 Kelvin. And our atmospheric pressure is an atmosphere, so we're good there. Except, let's see here, the question's telling us that we have, we're given the initial pressure in STP and we have a secondary pressure in atmosphere, so there's going to be a conversion here later on. So what I'm going to do first is I'm going to compare my starting conditions to my ending conditions. For this, we're going to use the combined gas law, and that is P1 V1 over T1 equals P2 V2 over T2. Okay, and again, the reason we're using this is because it's telling us that our oxygen is at STP and our carbon dioxide is at, we've got a different pressure and a different temperature here, so we're going to need to compare those because our volume is going to change as we go from STP to these other conditions. So I'm going to go ahead and plug in what I have. So I've got my 1 atmosphere, 0.465, that's going to be my initial volume, over 273.15 Kelvin, which is my starting temperature. Remember, 0 degrees Celsius is equal to 273.15 Kelvin. And now I'm going to put in my ending conditions, my carbon dioxide, so 0.973 atmospheres. We're solving for V2, and then our ending temperature is going to be 310.15 Kelvin. Alright, now when I do this, we're going to do my 1, I'm not even going to put that in, so 0.465 divided by 273.15. Okay, so that is the left side of my equation. Now I'm going to multiply over the 310.15, so times 310.15. Okay, now the only thing left is the 0.93 times V2. I'm going to divide out the 0.973, oops, missed to the 7. Alright, so our ending volume, V2, is equal to 0.542 liters. And my units here are going to be oxygen. So what I did is I took my oxygen at STP and I converted that to the other conditions, the conditions given for carbon dioxide, okay, these conditions. So my 465 milliliters of oxygen at STP is equal to 0.452 liters of oxygen at these conditions, right? Now, at this point, I'm in the same pressure, volume, temperature, sorry, not volume, but pressure and temperature as my carbon dioxide. So since they're the same, and they're both gases, I can just do my straight stoichiometry. So 0.542 liters of O2 times, my ratio is 5 to 3. So for every 5 liters of oxygen, I get 3 liters of CO2. And let me pull this back up. So since I have that saved into my calculator from before, I'm just going to multiply that by 3 over 5. And that gives me 0.325 liters, or 0.326 to be more exact, liters of CO2. All right, and that's how we do question 3.